In this video, I am going to talk about what a Hilbert space is. So you may have run across this term Hilbert space, named after the mathematician David Hilbert. And this video is also going to be quite informal and not rigorous. So if you're a mathematician, then this video might raise your blood pressure a little bit, but if you are not so mathematically inclined, then this will be a good jumping off point for the idea of a Hilbert space. So just sort of an intuition of a Hilbert space. So like I said, it's not going to be rigorous. It's not going to have the mathematical rigor that mathematicians so love, but it will be, as I said, a good jumping off point. And so to start talking about a Hilbert space, we first have to start sort of from the bottom and move our way up to the Hilbert spaces. So at the very bottom, I had got this figure here from Wikipedia, and I kind of like it because it's sort of exactly what I want to talk about. So at the very bottom, or the most broad, we have what are called topological spaces. And topological spaces, without any of these other things like the metric or the norm or the inner product, are essentially just a set, I guess you could say. So it's a set of points, and this set of points does have a few, I guess, axioms or laws that it obeys. And so, well, I guess we could say that a topology is, so it's a set of points, and we could call it maybe Tx. So it's the topology on some set x. So if x is our set of points, then the topology on x. So um, it's something that this set of points has. It's a property that this set of points has. And if we want to say x is equal to, we'll call this rectangle here our set of points. So it's full of a bunch of points inside here. And if we want a topology, then we have to say that the topology is something like, if we have our set here, then the topology are a bunch of subsets inside the set here, and these subsets obey some certain laws, and so we'll call these subsets, they're called open sets. And I'm not going to go too much into the difference between open sets and closed sets. Suffice to say that an open set is so if we have a circle, so say we're in some topology here, and we have this circle that's a subset of it, then the open set is everything inside the circle not containing the border of it, where a closed set is containing a border of it. So uh, I will say that if we have this here, then an open set I will draw as a dotted line, and a closed set is everything inside this circle plus the border of this circle. And as I said, I'm not going to get too deep into it and what's the importance of the difference and things like that. If you're interested in that, then I would look up point set topology. But this isn't a topology video, so I'm not going to get too deep into that. But anyway, we'll say that these are open sets, and the topology of this set here obeys these rules essentially. So if we have the union, which is often denoted by this large U here of the subsets. So I'll call the subsets let's go with y. So y are subsets of x. So this is the symbol for subset. If it's an element, we'll say that an element of it is p, and you'll see this little sort of maybe epsilon looking thing. So if p is one of these points in here, then this tells us that it's an element of x. If y is some open subset, so this could be p, and then this dotted circle is the subset. So p is a point and y is a subset. So the union of any sort of arbitrary subsets are all going to be an element of our topology here. And so a union is if we have this this open set and this open set, then the union is sort of the two of them together like this. And so then we also have the intersect of points, so or of subsets. Then these will also be so this has to be finite. So if the finite intersection, that will also be an element of our topology here, and the intersection. So if we have our two open sets like this, the intersection is this space right here. So we could say that that is just sort of the place where they are overlapping here. And so we also have the property that the null set is an element of the topology, and the whole set itself is an element of the topology. But anyway, this is probably as sort of formal as I'm going to get here. But essentially what we're saying is that we can draw a bunch of these open set circles in here, and the union, or in the union of any of them, will also be within this this topology here inside this rectangle, and the intersection of them will all be inside this rectangle here, which we're saying is our topology here. And so we can move our topology sort of further up by saying that it can also be separable, which if you're maybe a little bit more mathematical inclined, you might have heard of Hausdorff, which means essentially that you can, if you have a point here, we'll call it A, and a point here, we'll call it B, you can draw open sets around them that do not overlap with each other, and this we call separable. So these can be separable, and that gives us a little bit more structure to our topological space. But if we want to continue adding more structure, then we will add what's called a metric. So I'm going to move down here. So I put this here because, well, I'll get into that in a minute. So to kind of tell the difference between a metric versus a norm. And a metric essentially tells us, so if we have our topological space here with all our points inside of it, a metric can tell us that if there's a point here, A, and a point here, B, that there is some distance between them. So we could sort of map that onto a number line here and say that that there is some distance between them. And so that brings us to the norm, which is sort of another step up from metric. So if we go back here, so a metric space now has this sort of idea of distance in it that we did not have in our sort of more abstract topological space here. And so the metric, as I said, gives us this this distance here. But then we can also have what's called a norm, which sort of takes that distance and says that the distance is exactly this length. So we can, so if we have a distance, we could say A and B have this distance, and then we could maybe put another thing here that has D, and we could say, well, A to B is a longer distance than A to D. But we can't say for sure, well, how far is it from A to B and how far is it from A to D? So for that, we would need what's called a norm. So up here we have a metric, and then we have what's called a norm, and that tells us sort of exactly what the distance is. I mean, we have to sort of assign, I guess, what a basis to it, but we can say that there is such and such different distance between A and D and such distance between A and B. And so the norm is often just essentially the Pythagorean theorem. And so the norm, which you will see using the two lines outside of our variable here, is the Pythagorean theorem. So we have our x1 squared plus x2 squared plus dot 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 xn squared, and then we take the square root of that, and that gives us our norm. So I put this here because we can have a metric on these genealogies. We can say that that there is a certain distance from Diane to Ellen here. We say that the distance is sort of defined by having the same mother. But then we could also say there is a distance between Diane and Fiona here, which is sort of defined this way. And so that gives us a metric. We can say, well, these are sort of, maybe this is one away, and then this is maybe from Diane to Fiona is two away. But there isn't really a distance. We can't, I mean, we can say that there's a 1 and 2 away here, but when we can't say that there is sort of a distance that this actually represents. So what does it mean that these are two away? Is the two away from Diane to Fiona the same as from Diane to Grace? Is that the same sort of measurement between them? And so there is, it's kind of confusing, this idea between the difference of a metric versus a norm. And I thought this was maybe kind of a good way to think about that. But anyway, we'll keep moving on to the norm. And so the norm gives us sort of this this more clearer idea of distance, I guess. And one of the things about the norm that's sort of important, that's sort of the feature of a norm that sort of distinguishes it as the norm, is what's called the triangle inequality. So the triangle inequality. And this is essentially the idea that if we have a triangle here, so this is a right triangle, and we have one side that's A, one that's B, and one that's C, then the length of C is less than or equal to the sum of the lengths of A and B, which you can kind of see. If A plus B is going to be equal to C, then that essentially gives us a straight line, because then you sort of have to keep bending this down further and further until you get a straight line. And so that's called, it's called, I think, a degenerate triangle. But anyway, this is that triangle inequality here. And when you see it as a norm, it is often shown as A plus B is less than or equal to the norm of A plus the norm of B. But it's essentially just saying this, that that one side of the triangle, so this right here, would be kind of equivalent to the C on our triangle. Then this side is less than, or at the very most it's equal to the other two sides of the triangle, and that is that is how we can use our Pythagorean theorem that sort of imposes this idea of the Pythagorean theorem onto our space. And then the next step up is what's called an inner product space. So we have our metric, we have our norm, and then we have our inner product space. And as I said, in the sort of informal, non-rigorous way, you can maybe think of this as introducing the idea of angles. So introducing angles into our space. And so inner product is often sometimes called the dot product. And so that's a way that you can actually, it gives you, because sometimes also called the scalar product. But the scalar product or dot product essentially tells you if you have two vectors, then how much of this vector is sort of overlapping onto this vector. So it gives you the idea of angles between it. And so you need an inner product space in order to have the idea of what's called orthogonality. And so you need the idea of angles to have orthogonality. So orthogonal is if the dot product is 0. So if you have this vector dot this vector, then that equals 0. And so you need to know the angle between these in order to know that there is 0 overlap, because that would be something like this, where if this is our A here and this is our B here, you can see that none of A is overlapping over B, and so the dot product is 0. And so that's how we get orthogonality from the inner product space here. And then the next step up from that, well, not really, because this what's called the Binoc space. So Binoc space is well, it does not have an inner product space. Well, it's not an inner product space, or not necessarily an inner product space, but a Banach space is one that is complete. So it's a complete, and I'll get to that in just a minute. Complete normed vector or linear space. And so complete just means essentially that all the Cauchy sequences converge onto another element of the space. And so if we have our space here, if we take a sequence and start converging it, then it will converge onto a spot here in the space. But what makes it complete too is that if the point is on the border here, so that makes it closed, then any sequence will converge onto that space. Then that space on the border is part of the space here, and so that is a Banach space. So yeah, like I said, all the Cauchy sequences, which as we see here is a convergent sequence, will converge onto another element of that space. And so Banach spaces, so you may have seen, if you've tried looking up things like Hilbert spaces and so forth, so the L2 space, and I'll get into this in a moment. The more general version is the LP space, which is defined. This is the symbol meaning definition. So if we have a sum here going from n equals 1 to infinity, then we have the sequence. So all sequences form convergent series. So this is to the p, where p is greater than 1. And so this is these are Binoc spaces, these sort of scripty LP spaces like this, and they have the norm that is x n. We'll put a p there. So n equals 1 to infinity x n p, and then all this like that, which you can see is similar, is sort of a generalization of the Pythagorean norm that we were talking about. So that would be if we had maybe if we had x x3 here, p. Well, and we'll say that p is 2 in this case. And so that would be, we would have our x1 squared plus x2 squared plus x3 squared, and then the 1 over p would be 1 over 2, which is the same as the square root. And so you can see if we just get rid of that, we could do that. And so that is like our Pythagorean theorem. So this is sort of a generalization on this Pythagorean norm here. And then a Hilbert space is, well, this is the Hilbert space because, and I'm not going to prove it here. Like I said, this is informal, non-rigorous, but this is the only one of these that can be an inner product space. And so this is the only one that can have ideas of orthogonality and things like that. And so they are all convergent as well, just like we had up here. And so we would say that n equals 1 to infinity of x n squared is going to be less than infinity. So it's always going to converge. This just means that it won't diverge. So a divergent sequence might be something, well, it's going to be something that if you keep adding them up together, it will start it will approach infinity, where convergent means that it will not. It will, so if you see like this, it goes to, it moves to some finite number, whereas maybe if you had something that was like this, where it kept expanding, then the difference between here and here, compared to the difference between here and here, is going to keep getting larger and larger. So the difference between these two lines will keep getting larger and larger and will start going towards infinity. And so to be the Binoc space, then it has to converge, and then to be a Hilbert space, it has to be an inner product space. So it's a Binoc space that is also an inner product space, and that gives us our Hilbert space. And you will see Hilbert spaces in quantum mechanics quite often. So you may have heard that Hilbert spaces are often said to be, so it can be an infinite dimensional space, and that is not necessarily the case. So in things like in quantum mechanics, we have spin, which would be a 2D Hilbert space. Hilbert space. And so Hilbert spaces can go up to infinite dimensionality, but in quantum mechanics, you can use a Hilbert space of dimensionality that is required for for whatever you were trying to measure. So for spin, you end up with so if we have the spin like this, and I'll get into in later videos this bracket notation here, but we can have that be a linear combination of two states like this. So something like this. And so this is a two-dimensional Hilbert space because it's a linear combination of these two possible states. So maybe this would be spin down, this would be spin up, or however you want to define it. And we have things like our inner product space because we know that these can't, well, they don't have to be, but they can be orthonormal bases, so they can be orthogonal to each other. So we know that they have an inner product to them. And we have things like a metric and a norm and all that kind of stuff. And so something like this satisfies being a Hilbert space. And so it is a two-dimensional Hilbert space. And as I said, I will get into that more in future videos, but I just thought it might be, some people might benefit from having this sort of informal, non-rigorous introduction to the idea of the Hilbert space. And so I hope this video was somewhat enlightening to you. If you are interested in more rigorous and more formal expositions of this, I will have some links in the description down below. And anyway, I will see you in another video.